Hi, hello dear students. Welcome to physics class of PU2. We have been discussing the chapter atoms. In the previous video class, we have discussed the energy level diagram of an hydrogen atom based on the expression for the energy of an electron in the nth stationary orbit. And also we have discussed what is an atomic spectra, that is the types line absorption spectrum and line emission spectrum, and also the spectral series of hydrogen atom based on the energy level diagram. Now in the figure I have shown here the energy level diagram. So based on this energy level diagram, and you all know that what the energy of the electron in the nth stationary orbit for an hydrogen atom is given by En is equal to minus 13.6 divided by n square. So this is in terms of electron volt, right? So electron, in terms of electron volt, the energy is given by minus 13.6 divided by n square, where n is the principal quantum number, right? You know this. So if you put n is equal to 1 in this expression, you will get it what the energy of the electron in the first orbit of the hydrogen atom is minus 13.6 electron volt. And if you put n is equal to 2 in this expression, so you will get the energy of the electron in the second orbit, n is equal to 2 orbit, and in the second orbit the energy is given by minus 3.4 electron volt. So in this way, if you put n is equal to 3, 4, 5 and so on, you will get the energies as E3. For n is equal to 3 orbit, the energy is given by minus 1.5 electron volt and so on, right? So as the value of n increases, the negative value goes on decreases and becomes more positive, and for n is equal to infinity, the energy becomes 0, and hence the electron is no more bound to the the atom. It becomes free. The ionization of the electron takes place, right? Now here, what the next point we have to discuss here, the expression for the frequency or wave number of emitted spectral line, right? So all these, that n is equal to 1 state is called as what? The ground state, right? The n is equal to 1 state is called as what? The ground state. So in a normal hydrogen atom, the electron is in the lowest energy state, that is n is equal to 1 state, that is called as the ground state. Ground state means what? Its original state. In a normal hydrogen atom, the electron is in the lowest energy state, that is called as the ground state. That is n is equal to 1. And what happens when the energy is supplied to the atom? When the energy is supplied to the atom, the electron takes this energy and jumps into the higher energy state. So all these state 2, n is equal to 2, 3, 4, 5 and so on, all these states are called as what? The excited states, right? So therefore this n is equal to 1 state is called as the ground state, and all these remaining states are called as what? The excited states, right? In a normal hydrogen atom, the electron is in the lowest energy state, that is n is equal to 1 state, that is called as the ground state. And when the energy is supplied to the atom, the electron takes that energy and jumps into the what? The higher energy states, and those states are called as what? The excited state. But what happens? The excited states are unstable. Unstable means what? The electron, after a short interval of time, that electron comes back into what? Its lower energy state. So always in a lower energy state is a stable state. So what happens? That electron, after a short interval of time, that electron comes to what? Its ground state, lowest energy state. So during this transition, what happens? During this transition, the difference in the energy between the higher energy state and lower energy state is emitted in the form of electromagnetic radiation. For example, here the electron is in the n is equal to 1 state, n is equal to 1 state, and by taking the energy, it quantized energy, it jumps to what, n is equal to 2 state. But after a short interval of time, again it jumps back into what, its lower energy state, that is n is equal to 1 state. During this transition, that difference in the energy is emitted in the form of electromagnetic radiation. So now here we are going to derive the expression for that, expression for the frequency or wave number or wavelength of that emitted spectral line or emitted energy. So I think here the point is clear, what the expression we are going to derive here and what is the aim of our derivation here, right? Once again I will clarify it. Suppose the electron is in the n is equal to 1 state, right? It takes the energy. When the energy is supplied to the atom, the electron takes that energy and jumps to what, higher energy state. It jumps to what, higher energy state, right? That is called as the excited state, and this excited state is what, the unstable. So after a short interval of time, it jumps back to what, its original state, that is the ground state, lowest energy state. So the difference between these two energy levels is emitted in the form of electromagnetic radiation, that emitted in the form of electromagnetic radiation according to Bohr postulate, that is equal to what, h nu, right, where h is the Planck's constant. Now we are going to derive here the expression for this frequency nu, right? We are going to derive here what, the expression for this new frequency or wave number or wavelength of this emitted line or emitted energy. So that line is called as what, the spectral line. That energy is called as what, the spectral line. So when you observe this to the spectrometer, what we get here, the spectrum we obtain due to the transition between the different energy levels, we get the spectrum that is called as what, the line spectra of the hydrogen atom, line emission spectra. It is called as what, the line emission spectra of the hydrogen atom, right? So now let us start here the derivation. That is what, the expression for the frequency or wave number of emitted spectral line during the transition, what it takes place, right? So first point, let us consider here the two orbits n1 and n2, right? Let us consider here two orbits n1 and n2. So what are n1 and n2? n1 and n2 are the orbits of energies e1 and e2. These are what, the principal quantum number of that different energy levels, right? n1 and n2 having the energies e1 and e2. The energy of the n1 orbit is e1 and energy of the n2 orbit is e2. And now what happened here, e2 is greater than e1, that is e2 is the higher energy level and e1 is the lowest energy level, that is what we can call here the ground energy level, right? And here when the electron jumps from the orbit n2 to n1, that what we have given the example here, right? So n1 and n2, these are the two energy level. When this is n2 and this is n1, this is e2 and this is e1, alright? So what happens here, when the electron jumps from the orbit n2 to n1, the difference between these two orbits is emitted in the form of electromagnetic radiation. When electron jumps from e2 to e1, right, difference between these two energy levels is emitted in the form of electromagnetic radiation. So therefore, according to Bohr's postulate, what is that energy is given by what, right? According to Bohr's postulate, what we can write here, according to Bohr's postulate, what is the expression for that emitted energy? According to Bohr's postulate, the energy of that energy expression is given by what, E is equal to h nu, or h nu is equal to what we can write here, e2 minus e1, right? The difference between the two energy levels is emitted in the form of electromagnetic radiation, that is equal to what, h nu, e2 minus e1. And what is the energy of the orbit n1 and what is the energy of the n2? So that expression already we have derived. So what we can write here, the energy of the n1 orbit, that I can write here en1. So that is equal to what we can write here. So the expression is what, minus m z square e raised to 4 divided by 8 epsilon naught square, here n1 square h square, because n1 is the principal quantum number, the energy of the first orbit it is, that is n1 orbit we have taken here, right? And similarly for E2, what we can write here, En2 is equal to what we can write, only we have to change as the principal quantum number. So these derivation already we have completed in the previous classes, right? Minus mz square e raised to 4 divided by 8 epsilon naught square n2 square h square, right? So these are the energies of these two levels. Now we have to put these two values in equation 1. Now I will call this equation as 1. Now let us put these two values 2 and 3. Now let us put the values of 2 and 3 in equation 1. So now substituting these two values, that is the equation 2 and 3 in equation 1, right? Put these two values 2 and 3 in equation 1. So what we can write here, h nu is equal to e2 minus e1. So e2 we have to put equation number 3, in place of e1 we have to put equation number 2. So therefore h nu is equal to minus m z square e raised to 4 divided by 8 epsilon naught square n square h square. So n square means it is n2 square. Now in place of e1 what I will write, minus mz square. So here it is minus into minus is plus mz square e raised to 4 and divided by 8 epsilon naught square n1 square h square, right? So just by substituting the equation 2 and 3 in equation 1, so h nu is equal to, so first I will write this term, then I will write the this term. So by taking mz square e raised to 4 8 epsilon naught square and h square as common in both the equation, in both the terms, constant terms are what, mz square e raised to 4 8 epsilon naught square h square. Therefore mz square e raised to 4 divided by 8 epsilon naught square h square, it is taken common. So first I will write this term 1 divided by n square plus term, then minus term, it is minus 1 divided by n2 square. So this is what the equation we have got here, right? Now in this equation, this term mz square e raised to 4 8 epsilon naught square h square is a constant. All terms are constant here. M is mass of the electron, z is the atomic number, is charge of the electron, and epsilon naught is constant and h is constant. So now we are going to apply this for the hydrogen atom. So therefore let us put z is equal to 1 for hydrogen atom. Z is equal to 1 for hydrogen atom, and by putting z is equal to 1 I will take h to the RHS, it comes to denominator, therefore the frequency only is remaining here. Nu is equal to m e raised to 4 divided by 8 epsilon naught square, so h comes to denominator, it becomes h cube, right? H cube, and 1 divided by this is n1 square minus 1 divided by n2 square, right? And also you know that what nu is equal to c by nu is equal to what is the relation between the frequency and wavelength. So the relation between the frequency and wavelength is what, in terms of velocity of light, nu is equal to c divided by lambda. Let us put this value here. So therefore nu is equal to c by lambda. I will keep 1 by lambda here, and again I will take c to the right hand side, so it comes to denominator m e raised to 4 divided by 8 epsilon naught square c into h cube divided by 1 divided by n1 square minus 1 divided by n2 square. So this expression we have got now in terms of wavelength. So in terms of wavelength, what is the expression where this is the equation in terms of frequency, the frequency of emitted radiation, emitted electromagnetic radiation, you can calculate by using this equation, or the wavelength can be calculated by using this equation. So we have one more term is remaining here, this term. So this m e raised to 4 8 epsilon naught square c h cube. So all the values are constant here. all the values are constant. If you put all these values and calculate, we get the one constant term that is called as what? The Rydberg constant. So let us put here the constant term as a r m e raised to 4 8 epsilon naught square c into h cube. This constant is called as what? Rydberg constant. And by putting all these values, the mass of the electron, charge of the electron, epsilon naught, permittivity of free space, velocity of light, and the Planck's constant, by substituting all these values, and if you done the calculation, you will get the Rydberg constant value as 1.097 into 10 to the power 7 per meter. Right, so why per meter? We are getting the unit here. This is wavelength. It is a length, reciprocal of a length wave, so the unit is what? Per meter. Right, so finally the expression what we can write here, the 1 by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. Right, so 1 divided by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. So this is the expression for the wavelength of the emitted spectral line. So by using this expression, we can calculate the wavelength of the emitted line of any spectral series of the hydrogen spectrum here, or Lyman series, Balmer, Paschen, Brackett, and Peafan. So in this way you can calculate the wavelength of the emitted spectral line. And also we can represent this expression in terms of wave number. The reciprocal of wavelength is called as wave number. That is 1 divided by lambda is represented what? Nu bar. Nu bar is called as what here? The wave number. What is meant by wave number? It is the number of waves present in 1 meter length of the medium. Right, the number of waves, it represents what? The number of waves present in 1 meter length of the medium, that is called as what? The wave number. Right, so that is denoted by the symbol nu bar. Nu bar is equal to what? The reciprocal of wavelength, it is called as wave number. So in terms of wave number, the expression can be written as what here? So nu bar is equal to r into 1 divided by n1 square minus 1 divided by n2 square. So these are the three important equations we have in terms of frequency, right, in terms of wavelength, and in terms of wave number. So these three equations are used to calculate. So wavelength expression is used most in most of the time we use the expression of the wavelength and also the frequency. That is what? The wavelength of the spectral line. Right, in terms of Rydberg constant we have written here. Right, 1 by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. So here n1 is the initial state and n2 is what? The final state. So that the difference between the two energy levels, the transition takes place here. So n1 and n2 are what? The orbits of the energy levels. Between these two levels, the transition of electron takes place, and the difference between the two energy levels, that energy is emitted in the form of electromagnetic radiation. So hence finally we have derived here what? The expression for the wavelength or the frequency of the emitted spectral line. So then now, based on the expression for the wavelength of the emitted spectral line, now we are going to explain here what? The 5 spectral series of the hydrogen atom. Right, so whatever the expression we have got here, 1 divided by lambda is equal to r into 1 divided by n1 square minus 1 divided by n2 square. Right, where r is Rydberg constant and n1 and n2 are what? The quantum number, that is the principal quantum number of the lower energy state and higher energy state. So between these two states the transition takes place here. Right, now as you all know that the hydrogen spectrum consists of a large number of lines starting from what? The UV region to IR region. So here what we are getting in a hydrogen spectrum, the spectral series of the hydrogen atom, 5 series we get here depending upon the transitions. One is Lyman series, Balmer series, Paschen, Brackett, and Peafan. So all these series is having the specific transition between what? The lower energy state and higher energy state. Now let us discuss all these series with the specific transitions based on this expression, that is 1 divided by lambda is equal to what, r into 1 divided by n1 square minus 1 divided by n2 square. Right here, n1 is what, the lower energy state, and n2 is what, higher energy state. So here the transition takes place from what, n2 to n1. Right now, based on this, what are the values of n1 and n2, what are the values of n1 and n2 for these 5 series we have to discuss here. Right, and in which electromagnetic spectrum these series belongs, that also we have to discuss here. So first one, Lyman series. So in case of Lyman series, what is the value of n1 and what is the value of n2? So this Lyman series consists of again the spectral lines emitted by what, when the electron jumps from higher energy state to lower energy state, that is the ground state. And this series belongs to UV region. So there will be a 1 mark question asked in the examination, in which region of the electromagnetic spectrum the Lyman series of hydrogen spectrum belongs. That the answer is what, UV region. So it may ask in the CET also. Right now, what is the value of n1 and n2 for this Lyman series? So the value of n1 is 1 and n2 is what, 2, 3, 4 and so on up to infinity. So what happens in this case, Lyman series we can observe here. Right, so n1 is equal to 1, so electron jumps from the states 2, 3, 4, 5 and so on from the to the first state. Right, higher state to the lower state, the transition takes place, and here n1 is equal to 1 always for Lyman series. For Lyman series, always n1 is equal to 1 and n1 is equal to 1 and n2 is equal to 2, 3, 4, 5 and infinity. Right, in this way the transition takes place. So for Lyman series, there may be a transition from 2 to 1, 3 to 1, 4 to 1, 5 to 1 and infinity to 1. So in this way, that infinity is called as what, the series limit. That is called as what, the series limit. If the transition takes place from infinity to 1, that is called as what, the series limit. Right, so first transition is called as the first member of the Lyman series, and the last line is called as what, the series limit or last member of the series, what we call here. Right, Lyman series. So what are the values of n1 and n2 for Lyman series? n1 is equal to 1 and n2 is equal to 2, 3, 4 and so on up to infinity. So always n1 is equal to 1 for Lyman series. So always higher energy state 2, 3, 4 and so on to the transition takes place to first orbit. That is called as what, the Lyman series. Right, and this series belongs to UV region of the electromagnetic spectrum. Next, Balmer series. So here the electron jumps from higher energy state to n is equal to 2 state. Right, so again you can observe here the Balmer series. In case of Balmer series, always n1 is equal to 2, n2 is equal to 3, 4, 5 and so on up to infinity. Right, always n1 is equal to 2. So here the transition takes place from higher energy state to the n is equal to 2 state. Right, therefore n1 is equal to 2, n2 is equal to 3, 4, 5 and so on up to infinity. And this Balmer series, the Lyman series belongs to UV region, and this Lyman series belongs to UV region of the electromagnetic spectrum, and Balmer series belongs to what, visible region of the electromagnetic spectrum. This is also an important point here, that may also ask here 1 mark question in the examination. Right, so Balmer series belongs to what, the visible region of the electromagnetic spectrum. Right, so here Balmer series, always transition takes place from what, higher energy states to n is equal to 2 state. Lyman series, higher energy states n2 is 2, 3, 4, 5 and so on for Lyman, and n1 is equal to 1. Balmer series, n1 is equal to 2 and n2 is equal to 3, 4, 5 and so on in this way. Next, you can take here the next series, Paschen series. Right, in case of Paschen series, again it also consists of a spectral lines. When the electron jumps from higher energy states to the n is equal to 3 state. So therefore again here n1 is equal to 3. Right, n1 is equal to 3 for Paschen series, and N2 is equal to 4, 5, 6 and so on, the next higher energy states. So here again that transition takes place from electron jumps takes place from what? Higher energy states to n is equal to 3 state. N is equal to 3 states. The transition takes place here for Paschen series from the higher energy states. So that series is called as what? The Paschen series, and this series is belongs to what? IR region of the electromagnetic spectrum. So this is a very important point what we are going to discuss here in the today's class. So here we are going to solve the many numericals based on this concept here. This is a very important formula, that is the 1 by lambda is equal to r into 1 by n1 square minus 1 divided by n2 square. N1 and N2 represents what here? The transitions between the two levels. N1 represents always the ground state, that is N1 represents what? That is the ground state, and N2 represents what? Higher energy state, right? N2 represents what? Higher energy states, and N1 represents what? Lower energy state. Between these two states the transition takes place here. Next, bracket series, the fourth one, the bracket series. So in case of bracket series, again the spectral line is emitted when the electron jumps from what? The higher energy states to the n is equal to 4 state. So here n1 is equal to 4, right? N1 is equal to 4 here, sorry, bracket here, n1 is equal to 4, and n1 is equal to 4 and n2 is equal to what? 5, 6, 7 and so on, right? N1 is equal to 4, N2 is equal to 5, 6, 7, 8 and so on, higher energy state. So higher energy states to n is equal to 4 state, n is equal to 4 state, the transition takes place. Then we get the bracket series, and again the bracket series is belongs to what? IR region of the electromagnetic spectrum. So this is the fourth series what we are going to explain here, the bracket series. So again the n1 is equal to 4 here, n1 is equal to 4 here for bracket series, and n2 is equal to 5, 6, 7 and so on. So that is the empirical formula for all the series we can write here, right? Again bracket series, this series also belongs to what? Higher region of the electromagnetic spectrum. And the last one is P1 series. P1 series. So this series again consists of a series of spectral lines emitted when the electron jumps from the higher energy states to the n is equal to 5 state, right? N is equal to 5 here again. So n is for this empirical formula, if you apply, n1 is equal to 5 and n2 is equal to, n1 is equal to 5 and n2 is equal to what? 6, 7, 8 and so on up to infinity you can consider here. So very simple formula it is. 1 divided by n1 square minus 1 divided by n2 square into r, it is equal to 1 by lambda. So just by applying this formula and considering between these two, between which two states the transition takes place, considering that we can solve many numericals to calculate the wavelength of the emitted spectral line. For P1 series, what are the n1? N1 is equal to 5 and and n2 is equal to what? 6, 7, 8 and so on up to infinity. And this series also belongs to what? The IR region of the electromagnetic spectrum, right? So with short revision here, Lyman series, n1 is equal to 1, n2 is equal to 2, 3, 4, 5. If this transition takes place, you get the Lyman series. And what is the emitted line wavelength is or frequency is belongs to UV region. Balmer series, n1 is equal to 2, that is the n1 is equal to 2 and n2 is equal to 3, 4 and so on up to infinity. So n2 means what here? All these are the what? Higher energy states from which the transitions takes place to what? Lower state, that is equal to what? n1, right? So for Balmer series, n1 is equal to 2 and n2 is equal to 3, 4, 5. So 3, 4, 5 to transition takes place to n1 is equal to 2. Again for Paschen series, n1 is equal to 3. So higher states are 4, 5, 6. So here the transition takes place from what? These higher states to n1 is equal to 3 states. So similarly bracket series, higher states are 5, 6, 7, 8 and so on. From these states to transition takes place to what? n1 is equal to 4 state. And P1 series, the higher states are what? 6, 7, 8, and from these states to what? The transition takes place to what? n1 is equal to 5 state, that is n is equal to 5 state. So in this way we are going to explain here the 5 series of the what, the line emission spectra of the hydrogen atom. Very simple. We have the 5 series here: Lyman, Balmer, Paschen, bracket and Pfund. Lyman belongs to UV, Balmer belongs to visible, Paschen, bracket and Pfund are belongs to what, the IR region of the electromagnetic spectrum. Okay, with this discussion, that is the expression for the frequency and wavelength of the emitted spectral line of hydrogen atom, and explaining the 5 spectral series of the hydrogen atom: Lyman, Balmer, Paschen, bracket and Pfund. So we will stop here. We will continue in the next video class with the next points related to this topic. That is, I'm going to solve the numericals based on this calculation of wavelength of emitted spectral line of the hydrogen atom. Okay, we will discuss the numericals in the next class. Okay, thank you students.